Welcome to the first lesson in the AQA A-Level Physics series. We're kicking off with particles and the nucleus, what atoms are actually made of and the forces that hold them together. Here's where we're headed today. Before any of the physics, a bit of housekeeping that will save you marks in every single paper. Prefixes. Physics deals with things that are unimaginably tiny and unimaginably huge, so rather than writing that a nucleus is 0.14 zeros and 3 meters across, we use prefixes as shorthand. The key pattern to burn into your memory is this. We go up in powers of 1,000. Each step along this line multiplies by 1,000. Going down from your base unit, milli is 1,000th, micro is 1,000,000th, then nano, pico and femto, which is 10 to the minus 15, the scale of the nucleus itself. And going up, kilo is 1,000, then mega, giga and tera. Learn this line. When a question hands you nanometers or megajoules, you want that conversion to be automatic, not something you're nervously deriving under exam pressure. Also note that for micro, because we've already used the letter small m, we use the symbol mu. So how do we describe one particular nucleus on paper? We use nuclide notation, and you'll see this symbol everywhere. The letter in the middle, X, is just the element symbol, C for carbon, He for helium, and so on. The bottom number, Z, is the proton number, how many protons are in the nucleus, and the top number, A, is the nucleon number, the total number of protons and neutrons added together. Nucleon is just the umbrella term for a particle in the nucleus, so it covers protons and neutrons both, which gives you a handy trick. If you ever need the number of neutrons, you take the top number and subtract the bottom one, A minus Z. That's all there is to it. Now, two words that students constantly mix up, ions and isotopes. Let's make sure that we know what they both are. An ion is the same element that has gained or lost electrons, so it ends up with an overall charge. The key word there is same element. The proton number Z hasn't changed. You've just added or removed electrons on the outside, and that's what gives it a charge. An isotope, on the other hand, is the same element with a different number of neutrons. So again, same Z, because the moment you change the number of protons, you've changed the element entirely, but a different number of neutrons, which means we have a different nucleon number A. A quick way to keep them straight. An ion is about the electrons and the charge. An isotope is about the neutrons in the nucleus. An example of a hydrogen ion is H+, and an example of an oxygen ion is O2-. Different isotopes of carbon are carbon-12 and carbon-14. Next, a small idea that comes up a lot in exams, specific charge. Specific charge is simply the charge of a particle divided by its mass, charge per kilogram, and its units are coulombs per kilogram. That's the whole definition. One fact worth remembering is that, of all the common particles, the electron has the largest specific charge, and that makes sense when you think about it. The electron carries a full unit of charge, the same as a proton, but it has a tiny, tiny mass, nearly 2,000 times lighter than a proton. Small mass on the bottom of that fraction, big number out. So, charge over mass, coulombs per kilogram, and the electron wins. Now to the interesting question. A nucleus is a bundle of positively charged protons crammed together, and like charges repel. So why doesn't it just blow itself apart? To answer that, we need the forces. There are 4 fundamental forces in nature, but inside the nucleus only 2 really matter, and I'll tell you why the other 2 don't. First, the strong nuclear force, the glue. This is what holds the nucleus together, and it has a very particular behaviour with distance that you need to be able to draw. Look at this graph of force against separation. Between about half a femtometer and 3 femtometers, the strong force is attractive. It pulls nucleons together. Beyond about 3 femtometers, it drops to virtually nothing. It has an incredibly short range. But here's the clever part. Closer than about half a femtometer, the force flips and becomes repulsive. It pushes back. And that is essential, because it's what stops the nucleus collapsing in on itself. so the strong force holds the nucleons at a comfortable spacing, not too close, not too far. The second force that matters is the electromagnetic force, and this is the one trying to tear the nucleus apart because it repels the like-charged protons. It attracts unlike charges and repels like charges, and it follows an inverse square law. Its strength is proportional to 1 over r squared, so it weakens with distance, but it reaches much further than the strong force does. And the other two? Gravity and the weak nuclear force are the remaining fundamentals, but inside the nucleus they're basically irrelevant. Gravity, because the masses involved is so tiny, and the weak force only really shows up in decay. So some nuclei are unstable, and to become more stable, they decay. They throw something out. There are 3 types of decay you need to know: alpha, beta, and gamma. Alpha is the most ionizing, gamma the least, and each type changes the nucleus differently. Alpha throws out a whole chunk, a helium nucleus. Beta involves a proton and neutron converting into one another, and gamma is the nucleus shedding excess energy as a high-energy photon, without changing what it's made of. There's one more particle to introduce here, because it turns up in beta decay, the neutrino. When beta decay was first studied, the numbers didn't add up. Energy and momentum seemed to go missing, but we can't have that. The neutrino was proposed to fix exactly that, and its whole job, for our purposes, is to balance the books, to conserve energy, momentum, and lepton number in beta decay. And that word balance is a real skill in this topic. Every nuclear equation you write has to balance. The nucleon numbers along the top must add to the same total on both sides, and the proton numbers along the bottom must too. Practicing those balanced equations until they're second nature is one of the very best uses of your time here. The last idea for today, and it's a big one that we'll build on massively in later videos, the photon. Light isn't delivered continuously. It comes in discrete packets, and each packet is called a photon. I like to picture a photon as a tiny flying needle of energy. The important consequence is that energy can't be delivered in amounts smaller than one whole photon. Different photons carry different energies. A photon of blue light carries more than the photon of a red light. But you can never halve a photon. It's all or nothing, one packet at a time. This is what we mean when we say that a photon's energy is discrete. And there are 2 equations that go with photons, both of which you must know for exams. The first links the speed, frequency, and wavelength of light. C equals F lambda. The speed of light equals frequency times wavelength. The second gives the energy of a single photon. E equals HF, where H is the Planck constant and F is the frequency. And because C equals F lambda, you could rewrite that second equation as E equals HC over lambda, for when a question gives you the wavelength instead of the frequency. Same equations, 2 forms. Just pick whichever matches the numbers you've been given. And that's the end of the first lesson. Make sure you really nail these topics as they're so important as a foundation for the rest of the course. Thanks for watching, and make sure you check out my tutoring page.